Hello friends, today we will discuss very fundamentals of queuing theory. What are the essentials of queuing theory? Detailed description we will take up in the next session. Queuing theory describes the behavior of a system that provides services for randomly arising demand. And the fundamental idea of queuing theory is that congestion occurs due to delay caused by an interruption in a flow system. The flow is usually discrete, it is random. For example, arrival of vehicles at a toll booth, but it can be continuous also. Like the traffic flow from the stop line of a signal control intersections after traffic light turns green. To specify a queuing system, 5 aspects must be known. And the first is the input function. Input function. That is the arrival. Arrival of items. The second is input source. Input source, whether it is finite or infinite. Very common case is of infinite source, means the vehicle are arriving and the source of arrival is infinite. But there can be finite source also. I will tell you little later what is that finite or infinite service. Then third is queue discipline. Queue discipline. How these arrivals are being served, what is the pattern of service. And there are 2-3 types of discipline. One is first come, first served, which is the most common type of discipline. This is also called FCFS or FIFO, FIFO, first in, first out, or first come, first served. Again, we'll take the example of a toll booth. A vehicle which is first in the queue will be the first to be served by the system. But there can be some situations where this queue discipline is last in or last come, first served. This is also called LIFO, last in, first out. And this type of system you can imagine, for example, a crowded bus. When you enter a crowded bus, you are the last person to stand in the crowd. When the bus stops at the station, then you will be the first to be out of the gate. So that is last in, first out. Maybe you can take one more example. When the items are placed one above the other, and when you remove them one by one, so the last item which was the top will be removed the first. So that is the example of queue discipline. The fourth is channel configuration. Channel configuration. How many service channels are being provided? It can be 1, it can be 2, 3 or n. It all depends upon the demand. And last one is service time distribution. Service time distribution. How the service time is distributed. So generally what is assumed in traffic engineering, that arrival, that is input function, is random, but it can be deterministic also. Not necessarily probabilistic, it can be deterministic also, uniform arrival also. Queuing theory generally revolves around 3 types of distributions: random, uniform, or Erlang. This is M, this is D, this is E. That is how it is represented in the queue discipline or queuing theory. Input source can be finite or infinite. I told you the population can be infinite in case of a arrival of vehicles at a point. So the source is infinite. The population is infinite. It can be finite also when you restrict the number of arrivals. For example, you go to a mechanic shop, then there will be, let us say, 2 mechanics which will be repairing the automobile, and maximum 2 can be in the waiting line. So the source is now very limited. So that becomes finite source of population. Queue discipline, I told you, channel configuration can be a single channel or it can be multiple channels. In case of a single channel, now these are the arrivals and here is the service channel and this is the output. Out, in, and this is the service channel. That's a single channel process. So arrival is random, M, service channel is 1. Now the service time is also distributed randomly, so it has exponential distribution of service time, and this is the output. So this is the queuing discipline MM1. First M basically indicates the arrival, the second the service, and 1 is the number of channels. In the case of multiple channels, this configuration that you have arrivals and for each arrival you have a service channel and this is out. Another queue here and you have another service provider here and that is out. This is also a case of multiple channel. It can be n number of channels. But important point here is that once a arrival joins the queue, it becomes a simple case of a single channel. The arrival here may be common arrival. Common arrival, a vehicle is arriving here and it can join this queue or it can join this queue or it can join this queue. But once it joins the queue, then it becomes a case of the single channel. The arrival is divided into 3 parts. Okay? Outcome is also in 3 parts. So total outcome or total output will again be a single output. That is a case of multiple channel. Or it can be that you have a single queue here and then these arrivals, basically they will take and you have multiple servers here and it will go to any server, whichever is empty, it will go to any server. This is the case, and then you have output out from each server. In queuing theory, the arrival rate is taken as lambda and output departure rate is taken as mu. Lambda is considered to be random, mu is, or you can say service time is exponentially distributed. Now here in this case, this will be mu, this will be mu, this will be mu, this will be mu for each server. Lambda is divided now into 4 parts. So lambda, common lambda, output is 4 times mu. That is the case of multiple channel queuing problem. So in queuing theory, we consider the arrival rate lambda, and departure rate mu. Mu items per hour. It can be vehicle also, it can be persons also, per hour. Now this lambda upon mu, that is the utilization factor. Now if this is less than 1, then that is called a undersaturated condition. Undersaturated condition. If it is lambda by mu is 1, that is saturated condition. And if it is more than 1, it is oversaturation. For a infinite population and finite Q, this condition must be satisfied, that lambda upon mu should be less than 1. Now, for example, let us say you take the rate of arrival on a service window, 600 vehicles per hour. What does it mean? 600 vehicles are arriving in 1 hour. So on an average, you can expect that there will be one arrival in every 6 seconds per item or per person. And departure rate mu is 900 vehicles per hour. That means service rate or the service time is around 4 seconds. 4 seconds per vehicle. Now the very first question comes in mind is that if the arrival is smaller than departure, why should a queue build up? Remember that this is the average time, 6 seconds, but not necessarily that every 6 seconds there will be a vehicle. Sometimes it can be in 1 second also, it can be in 2 seconds also, it can be in 8 seconds also. Because of randomness in the arrival, the queue will always build. Service time is more or less constant, 4 seconds, so output is 900 vehicles per hour, and therefore there will always be a queue. But if you take a case when lambda is 900 vehicles per hour and mu is 600 vehicles per hour, then in that case, this utilization ratio, lambda upon mu, is 1.5. This is what is called the rho. We denote it by rho. Now here, this is a oversaturation condition. So on an average, there will be a vehicle in 4 seconds and it will take 6 seconds to be processed, to be serviced, and therefore in this case you can consider that every 1 hour 300 vehicles will be joining the queue, and a vehicle which joins the queue at any time will not be served, and therefore for infinite source and finite length of the queue, this must be less than 1. So in addition to that, there are 3 more characteristics of the queue. One is bulking. Now take an example. Suppose you go to a railway station for reservation of a ticket, and there are 3 windows, and when you reach there, you find that there is already 15 person in the queue, and you decide not to join the queue because queue is too long. So you quit and you decide either to book the ticket online or come sometime later. That is called bulking. When queue is too long to join, or the waiting time is too long to join the queue, then it is bulking. But this is the perspective of the person. Now this is what we call unforced bulking. But there can be forced bulking also. Forced bulking example is that Suppose you want to work on a system, you go to the computer lab, there are 20 systems, all systems are occupied for next half an hour, and therefore you go back. That is the balking forced by the system. The second is reneging. Now, reneging is that the same. If you take the example of the same reservation counter, you join the queue. And after, let's say, a few minutes or maybe after 10 minutes, you find that the movement of the queue is very, very slow. You have another work to do after half an hour or 1 hour, so you decide to quit. So that is reneging. Reneging, the difference between balking and reneging is that balking is quitting before joining the queue. Whereas reneging is, after you join the queue, you experience some delay there and then you go. And the third is joking. Joking. Now, in joking, what happens that in case of multiple channels, suppose you take a case of 3 channels and there are number of persons in each queue. Now, when a person arrives here, let us say there are 12 persons here, there are 10 and there are 15. When a vehicle arrives, this vehicle joins the queue, which has 10 number of vehicles. But after joining this queue, it finds that this queue is moving very fast. So after some time, he moves to this queue. That is called joking. So joking is leaving the queue in between and joining other queue because the other queue is moving faster. So if you ignore balking, reneging and joking, there can be 4 types of queue disciplines. Whether you have a single server or multiple server. You have infinite queue length or finite queue length. That will produce 4 queuing models. Single server with infinite queue or infinite source, single server with finite queue length, multiple server with infinite, multiple server with finite length. Now, single server with random arrival, random service rate, 1 server, infinite population, infinite queue length. That is how it is. Infinite queue length and infinite population. That is how it is written. A single server model with random arrival, random distribution of service time, 1 channel, infinite queue length and infinite population. The rate of arrival is taken as lambda and rate of departure is taken as mu, and this lambda upon mu is the utilization rate, which is denoted by rho. The interest here is what is the expected number of items in the system, what is the queue length, what is the waiting time in the system, and what is the waiting time in the queue length. What is the probability that there will be no arrival or no item in the queue, or what is the probability that there will be no item in the system? One thing you should note that the collection of arrivals waiting to be served is called the queue, but the number of items waiting to be served is called the queue length. So when you say there is a queue, it does not specify the number of items in the queue. It only specifies that there is a queue to be served. But the moment you say there are 10 vehicles in the queue, that indicates the queue length also. So in this session, I have told you the essentials of queuing theory. In my next session, we will discuss the problem of MM1 and how to get all values of expected number of arrivals, expected number of items in the queue, queue length, service time, waiting time, all those parameters we will calculate in my next session.